So that's the rate
I'm with you.
of photons hitting. So then we have that formula for n now. We plug that in, which is I times A divided by E.
And then this stuff carries over. I like it.
Yeah. And then next line is we plug in for P and E of the photon.
P
Momentum of,
was h over lambda. Energy of the photon with hc over lambda. So then you get an hc over lambda on the bottom. So you flip it.
Yep.
P is h over lambda. Yep, looks good.
Yeah, and then the h's and the lambdas cancel, surprisingly.
Very nice.
Which the next line leaves 1 over c on the very right. Everything else is the same. And that's our equation. If we want to know the force on the solar sail, the way we've done this here, we know the intensity of the sunlight at that particular distance times the area of the sail, and then multiplied by this thing that takes into account how much is reflected and absorbed.
This material factor?
By C. Yep. Then we get the total force.
Cool.
On the solar sail. Cool. So we got a couple calculations here. What if we said we're going to make a solar sail the size of a football field?
Okay.
Which is about 10,000 meters squared.
Okay.
At Earth distance. So plug in some numbers here. What kind of force do we get?
Wait, where's the Earth distance coded here?
So Earth distance, so if you're really close to the sun, the intensity of sunlight will be really high.
Okay.
If you're far away from the sun, the intensity of sunlight will be really low.
I see.
We have to,
The Earth distance is encoded in the intensity. I see. So if we were on Mercury, this would be a huge number.
Yeah.
I see. And then you looked it up, and this is whatever it is. Okay. I'm with you.
Yeah. So 1316 watts per meter squared, that's the intensity of sunlight, multiplied by the area of the football field.
Yep.
Is that right? 100 meters by 100 meters? That's a little bit bigger than a football field, but okay.
Okay. Whatever it is.
And then 1.7, that's 1 plus 0.7. That's our materials properties.
Yep.
And then the divided by C at the end there.
3 times 10 to the 8th meters per second, but it's upside down, so okay.
Yeah, plugging that all in, we get 0.07 newtons.
Okay, what is this? Wait. What is this? What is it? Okay, give me like a scale I can understand.
Okay, so 1 kilogram is 10 newtons.
Yep.
Because 1 kilogram times 10 meters per second squared is a newton.
Yeah, so that's m times g. Okay, g is 10, close enough, sure. 10
Which means, how much is a pound? A pound is like 25 newtons.
Okay, yeah, because one kilogram is about 2 pounds.
So opposite direction, I got that wrong. It's about 5 newtons per pound. So 10 newtons per kilogram, about 5 newtons per pound.
Okay.
Roughly.
So if I were to lift a 1 pound weight, I should get 5 newtons, and this is significantly smaller. So this is real like nothing. Real small.
Yeah,
Okay.
Real small. So aerial football field ain't gonna do it at Earth distance.
Yeah.
So then the next calculation is, okay, there's not enough force to do this. So then I said, okay, what if I want a jet engine force? So like a jet engine on an airliner.
Yep.
Look that up. How big would the solar sail need to be to get jet engine force? So we plug in.
Yep, and we're going to go to overleaf because I didn't copy that part.
Oh. Okay.
We're back in the game.
So the area of the so we rearrange the equation now. So the area of the sail.
Area of the sail. So I move everything to the other side of the equation, which means it's F over everything else.
Yep.
1 over C. So I get
that's.
Yeah. So I get FC.
So FC. Yeah, go ahead.
So you get FC over everything else. Seems good.
Yeah, and then plug in force, 500 kilonewtons. I think that's right for a jet engine. Multiplied by, I had to look that up, multiplied by C, divide by the intensity of sunlight, divide by that materials property, 1.7, gives 6.7 billion meters squared, which is 6.7 thousand kilometers squared, which is big.
What the? I guess. Like, what is? Okay. What is this in a scale that I recognize?
So this is the size of the state of Delaware. We looked it up.
Okay, we got that. Oh, hey, we left it up. Nice.
Actually, can we find a European country that's about that size? Well, how big is Belgium?
Area of European countries in KM2.
Okay, here we go.
KM2 sorted by this. So we're looking for what number?
6,000.
6,000.
6 to 7,000.
7,000. Hey, Azerbaijan.
Azerbaijan.
A little bit smaller than Kosovo.
Somewhere Azerbaijan, Kosovo. Or let's see, how big is Belgium? So Belgium is 30,000. So we're looking at
five
a
Belgians.
fifth of that. A fifth of Belgium.
Let's get a little map.
That's get a little mappy map. Yeah. So about a fifth of Belgium. It is big. That's pretty big.
Gosh.
Yeah. Fifth the size of Belgium. You have to make this material fifth the size of Belgium. Hook up all the tethers. Make sure everything is engineered
in order to have it pull like a A320 type plane. To have it for the spaceship to have similar characteristics, you'd have to have a solar sail on the size of Belgium for to have that type of acceleration.
Yeah.
Damn.
So you're
holy cow.
Limited. But the good thing is no friction in space, and you get this force happening over huge amounts of time. So you do get probably some pretty good speeds if you wait.
And yes, for completeness, for an American scale, we would be about the size of Delaware. So in the middle here, you'd have a little ship with all these tethers pointing out the outside to attach it. And then, that would get you airplane-like characteristics. But I guess what you exactly said, you don't have to worry about air resistance here in space. Mm-hmm. So you can just go faster, faster, and faster. There's no terminal velocity.
Yep. But as you move away, as you pick up speed and move away from the sun, the intensity of light goes down. And so your acceleration decreases.
That's a good point. This number will go down.
Yeah. So
cool.
I think there's been some talk that I've heard. Just proposals. Like you put a laser on the Earth and shoot it into space, pick it up to a power plant or something, and you have micro solar sails, and you can get this really intense laser beam from the ground. And you just aim it at the solar sail. Well, in this case, the light sail on your device, and then you get a pretty constant acceleration because you've got this tight beam of photons.
And it diverges a little bit, but it's pretty good. Yeah.
And you could probably calculate that divergence to create a large enough solar sail that you would know the characteristics as it goes out.
Gosh, and
so
you could do like a train.
Yeah.
So as a as a ship gets too far away, its solar sail becomes too small. Well, you just send up another ship to follow it, and you push that follower ship with the initial laser. Yeah, you get like a little caravan.
So if we want to get to Alpha Centauri, you got to run a train on Alpha Centauri.
That's right. Let's get everyone get on the train.
Let's get it going. Let's go.
Bang bang. Yeah, it'd be pretty cool.
And okay, so I think some difficulties with this calculation. One is the intensity decreases as time goes out, so the force depends on distance.
Yeah.
Also, this material properties and the spectrum of sunlight, which we have here.
That's true. I think you got that's what this is.
Yeah. So the material is probably going to reflect light at different percentages depending on the wavelength, depending on how you've created this material.
This is I recognize this. This is the blackbody radiation curve.
Yeah.
This is like the wavelength or frequency, how you want to think about it. The wavelength, the dependence of what are the characteristics of light that leave. So you get more red that leave the sun. You get more red light over here, more blue light over here, and the visible spectrum is like this tiny little sliver somewhere in there. But that's the point. There's the light that comes out of the sun has different energies, and so what you're saying here is in this number, this row reflected and this sunlight. These are both actually wavelength dependent.
I think so. Yeah.
So, for example, you said that this was, I think, if I remember, this is 70% of the light goes through a windshield, and so that's why you can't tint your windows depending on which state you're in. Okay, so but like if you had like a radio wave, like that goes through your entire car, like it doesn't care. So there's this row absorbed, this row reflected has a wavelength dependence built into it somehow.
Yeah.
Engineers need to
somehow
measure it.
Yeah, this 0.7 we calculated is somehow some overall we integrated out over the entire spectrum, reflecting on that material 0.7. But if we really want to do this calculation, we would have to do get the solar sail material, measure it for all the different wavelengths that sunlight is relevant for sunlight, and then we could then integrate the reflection coefficient, this rho, over all of the wavelengths to get the proper calculation.
And the same thing would be true for eye sunlight, if we wanted to have this is like a real coarse multiplication calculation, but if we wanted to get a bit more granular, a little bit more precise, this would be a DF, a little differential F. This sunlight would have a wavelength parameter, a lambda built into it somehow. The rho reflector would have a wavelength built into it somehow. And so you'd have a D lambda out here that you'd integrate the whole thing over.
Yeah.
Okay. Cool. Yeah, cool. Next steps of whoever wants to do this calculation carefully.
Yeah. I don't know if it would change. I think it would change the numbers, but I think there's still going to be big areas for required. I don't think you can move the needle that much, with actual calculations here.
But to get it precise, To get it precise, those are the next steps that I would take.
Yeah.
Cool.
Yeah.
Cool calculation.
So cool. Yeah.
Thanks for doing that.
Yeah. All right. Cool. See you guys next time.